All right, recording has started. So good morning, everybody, and welcome back to Math 115. Before we start, check in with my class. How's everybody doing today? Surviving? It's a good thing I checked because I can't see the meeting chat again. Oh, there we go, making it. Nice. Not too shabby. Okay. These things are showing up. They're just taking a really long time for some reason. Stressed but good. Hanging in there. Okay. Gotcha. Well, I hope you're not too stressed about this class. If you are stressed about this class, then I'd highly recommend that you come see me during office hours today. I have them from 9:30 to 11:30. So if you're worried about understanding the sorts of things that we've been talking about lately or anything else, please come and we'll chat, and it's not going to be too intense or anything. We'll just get you some help, okay? All right, well, glad to hear that everybody's at least getting by. Sometimes that's all you can ask for. Well, I will share the screen and then we'll get started with our lesson for today. Okay, so before we start a new topic, which the next topic we're going to talk about is going to be exponential functions, let's go back and review what we learned last time. So what we learned about last time was basically I kind of reviewed a little bit more about how to graph rational functions, okay? So rational functions, when we have a polynomial divided by a polynomial, how do we figure out where there are going to be asymptotes, where are there going to be wholes, where are there going to be zeros? And once we have all of those pieces of information, we can kind of draw like a not too shabby graph of what it's going to look like by just kind of filling in the gaps with a smooth curve. Okay, so that's what we do. And we had all these rules for when we're going to have a horizontal asymptote, when we're going to have a hole, and then for the vertical asymptotes, we had to, where did those go? Well, here they are. For the vertical asymptotes, we had all of these different types of behaviors here, which I did in green, blue, red, and purple. So depending on whether the value of the function, except for the zero at that point, is going to be positive or negative, and depending on whether the multiplicity of the zero is even or odd, then we're going to have one of these four behaviors. Okay, so this is just about how to draw the graph of the function, and that can be kind of useful in a lot of calculus settings, or even just manipulating these rational equations in just an algebraic setting. Okay, we want to know sometimes where are these things blowing up, right? If these curves are describing something physical, right, or something somehow meaningful to the real world, like dollars and cents, or I don't know, COVID case numbers or something like that. If we can model these with rational expressions and we see things blowing up, that has a physical meaning. If something's blowing up to negative infinity, that might mean that we're losing a shitload of money, excuse my language. Or if we're, blowing up like this blue thing on the left side here, we might be like having COVID cases going through the roof, and then our civilization collapses. So, these things have an actual physical meaning when this blow up happens. So it's good to understand how we graph these functions. Okay, so then once we kind of got a handle on how to graph these things, we started talking about polynomial and rational inequalities. Okay, so the way we solve these is basically by getting everything on one side and factoring it completely and writing it as a single expression, and then we just find the zeros, plot them on the number line, and we choose these test points from each interval. Okay, choose these test points from each interval. Okay, so we had one example with this cubic polynomial, and really the hardest part about that one was just once we had everything on one side, how do we factor it, right? And with a cubic polynomial, the way we factor it is we have to guess a factor, okay? So we guess a number which is going to give 0 when we plug it in, and we can kind of see in advance that that's going to be 1, just because we see if we plug in 1, we'd get, 1 plus 3 minus 9 plus 5 is 0, okay? And then we just divide out the corresponding factor using long division, and we're left with a quadratic function. So to factor it the rest of the way, all we have to do is factor that quadratic. And then we wound up with this expression here. And then all we did was we just plugged in test points from each interval. Okay, so we picked 1 point, which was to the left of -5. We picked 1 point, which was between -5 and 1. We picked 1 point, which was to the right of 1. And we found out, okay, where is the inequality working and where is the inequality not working? Okay. And then finally, since we had a strictly larger than sign here, that is why we filled in, or we didn't fill in, I should say, our dots on the actual zeros. Because we know that if we plug in x equals 1 or x equals -5, it's actually going to make the thing equal to 0, right? That's what would happen if we plugged in one of those numbers. And we want to know what x values can we plug into this function and get something which is strictly larger than 0, okay? And since 0 is not larger than 0, we don't include those points. Okay, so that was how we did that one. And rational inequalities weren't too much harder. Okay, the only thing we have to do is there's a couple things we have to do extra. First of all, we need to get everything on one side and write it as a single fraction, okay? We have to write it as a single fraction. And then we factor the top and bottom completely, and then we plot the zeros of the top and the bottom on the number line, and we pick a test point from each interval as usual. And then we figure out whether we should have closed dots or open dots depending on whether or not we have a and equal to or equal to sign on our inequality. And we had to be careful about one thing, which was that if once we get everything onto one side and express it as a single fraction, we need to remember that the zeros of the denominator should always get an open dot. So let me say something really quickly about why that is the case. And to do it, I'll draw your attention to our fully factored expression here, which I've boxed in green. Okay, so once we had this thing fully factored, what we're trying to say is we're trying to describe which x values can we plug into the left-hand side such that when we plug it in and we do the subtraction and we do the division and the multiplication in the denominator, and we do all of that stuff, we get a number which is larger than or equal to 0. Okay? And the reason we should have an open dot on the values 1 and 2 here is because if I were to plug 1 into this expression, I would get -2 divided by 0 is greater than or equal to 0. And we're trying to evaluate whether this is true or false. And basically, the left-hand side is nonsensical. Okay, so the reason this is false is because, I mean, you can't even really explain what the left-hand side even is. It's not defined. So the question of whether it's larger than or equal to 0 is moot, as it were. Okay, so that's why we have the open circles on anything which is going to cause the denominator to be 0. And then the reason we had a closed circle on 3 was because of this greater than or equal to sign, okay? Greater than or equal to sign. Because if we plugged in 3, it would make the top 0 and the bottom would not be 0. So 0 divided by anything is 0, which is larger than or equal to 0. Okay, so that was about the rational inequality. And again, we just pick test points from each interval and we check and see. We plug them in and we see, does this give me something which is true? Does it make the inequality true? If so, we fill in everything in that region. If not, we don't fill in everything in that region. Okay, so before we move on to something new, let me do one final example here to demonstrate what this test point business is really doing. Okay. And I'm going to demonstrate this using the graph of a function, okay? So here we have a quadratic inequality. We have x squared minus 17x plus 72 is larger than 0. Okay, this is what we're trying to figure out. Okay, a lot of the times what they'll do actually is they'll give you something like plus 71 is larger than or, oops, that was supposed to be a 1. 71 is larger than -1 or something like that. And they'll make you move it over and they'll say, okay, yeah, you got to remember that you got to move everything over. 17x plus 72 is larger than 0. Okay, so that's first step, is always get everything on one side, right? And then the second step is always to factor this thing completely. Okay, so we factor it. We want two numbers which are going to sum to -17 and multiply to positive 72. What do we think? How should we factor this left-hand side here? On two numbers that sum to -17 and multiply to positive 72. Okay, here we go. Now they're coming in. For some reason I'm not getting the audio cue anymore. Okay, sweet. We got 9 and 8. Yeah, x minus 8, x minus 9. Yeah, perfect. Okay. So yeah, we want to make sure that they're negative, right? Because they should sum to -17. Okay, so we need the negatives. So -8 and -9. Very good. Okay. And then the next step, right, would be to put these on a number line. We'd put 8 and we'd put 9, right? Because those are the corresponding zeros, right? The zeros are going to be whatever we plug in for x to make this 0, right? X minus 9 equals 0. That means x is equal to 9. Okay, so we plot our zeros on our number line, and now what we want to do is pick a test point from each thing here, right? So I'll pick, I don't know, I'll pick 0 just because that's easy to plug in. And then I'll pick 10 maybe. And then in the middle, I'll pick 8.5. Okay, so I plug in 0, I get 0 minus 8 times 0 minus 9 is larger than 0. Okay, and I get -8 times -9 is 72. So yes, that's larger than 0. So this region here is going to be all good. Now let's try 8.5. If I did 8.5 minus 8 times 8.5 minus 9 is larger than 0, I would get 0.5 times negative 0.5 equals negative 0.25. And that's not larger than 0. So this region is going to be all bad. And then for the last one, we'd have 10 minus 8 times 10 minus 9 would be equal to 2, which is larger than 0. Okay, so again, this region on the right-hand side is good. So finally, what I would do is I would use my, green pencil or whatever. I guess I should use a different color now because I'll use purple since the number line's green. I would, fill in this whole region to the right of 9. I'd fill in this whole region to the left of 8. I would not fill in the region in the middle. My question to you guys is, should I put an open dot or a closed dot on 8 and 9? What do we think? Okay, I'm seeing somewhat conflicting answers here. Seems like more answers coming in for open here. Somebody who said open, want to explain why we should choose open? You're correct. We should choose open. But why? Yeah, I think Heidi's really hit it on the head. When we want to decide whether we should have an open or a closed dot on 8 and 9, okay, on our zeros, we need to check this sign right here. Since our sign is sort of missing this critical or equal to part, right? If we had that pink piece there, then we would have a closed dot. But since we don't have that pink bit, okay, we've just got a strictly larger than 0. You can actually test and see if I should have a closed dot on 9 by plugging 9 in. You'd get 9 minus 8 times 9 minus 9 is larger than 0. And you're trying to evaluate whether this is true or not. Well, this would give us 0 is larger than 0. And 0 is not larger than 0. So we don't fill in that dot. I guess I'll go back to purple. Okay, so we don't fill in those dots there. Okay, so when we see a greater than or equal to sign, we should be thinking closed dot. When we see a greater than sign, we should be thinking open dot. Okay, or if we're also less than or equal to or less than. Oops. Okay, so these are the signs that go with the closed dot and the signs that go with an open dot. Yeah, Savannah had the same answer. There's no equal to sign included in the greater than sign. Very good. Okay, so yes, I've done another example here, but what I really wanted to do this for was to demonstrate, okay, what we're actually doing with this number line here, okay? If I were to take the function f of x equals x minus 8 times x minus 9, what would it look like? Well, I know it's a quadratic function. It should be a parabola. It should open up because the coefficient on x squared is a positive number, in our case, positive 1. So this should look like a parabola with zeros at positive 8 and 9. And it opens up. Well, what does such a parabola look like? It has a 0 at 8 and a 0 at 9, and it opens up. Well, it should be coming down, down, down to 8, and then it should briefly pass underneath the x-axis, and then it should go up again. Okay, so I want to explain what is the physical meaning of what we did here. Okay, well, I guess not physical meaning, but graphical meaning of what we did here. We picked a test point to the left of 8. We picked 0, okay? So we picked this point 0 here, and we plugged it into the function, and we checked what is the height of the function. And we found that the height of that function was 0, 72. That was the point on the function, okay? So we would, if we were to draw this whole parabola out, it would look like that, right? It's just saying that when we plug in that test point over to the left, we got something which was above the x-axis. And we know that the function is going to remain above the x-axis until it passes through a 0, okay? So that's why I'm able to determine that this entire left side of 8 here should be filled in, okay? Because I know that there's no way that it can stop being above the x-axis until I hit a 0, okay? And even then, it still might not go beneath, okay? But that's definitely a necessary property, okay? And then we had this region here in the middle, okay? We picked 8.5. So what is the physical or the graphical meaning of that? The graphical meaning of that is I took this function f of x equals x minus 8 times x minus 9, and I took the x value, which is right here at 8.5, and I plugged it in. And what did I get? I got a negative number, and this is the ordered pair 8.5 comma, I don't remember what we got, 8.5 comma negative 0.25. Okay? And I know, okay, I know because this point is beneath the x-axis, I know that it's going to be beneath the x-axis at least until I hit one of my other zeros. So that's how I'm able to know that this entire middle region should be in red. And then likewise, I just picked another point here. I picked the point 10, and when I plugged it in, I got the point 10 comma 2 on the graph. Okay, and I recognized that that ordered pair lies above the x-axis. Okay, and so that's how I knew that this whole region to the right of 9 gives us positive values. Okay, so that's one graphical interpretation of what we're doing. In fact, if you want to just draw the graph and say, well, clearly from the graph we can see that it's going to be positive to the right of 9 and to the left of 8, then that's perfectly fine too. Okay, that's a fine way of reasoning. But the test point method is a bit more comprehensive, and it works with functions which you don't even know how to graph, like a rational graph. Okay, so say you're totally confused by my lecture on how to graph rational expressions. You don't need to know how to graph the rational expression to use the test point method and determine where the graph is going to be positive or negative. Okay, you just need to know how to combine fractions and factor polynomials and then plug things in, right? So that's one advantage of the test point method over the graphical method. Of course, if you have the graph, then it's really quite easy to see where it's going to be larger than 0 or less than 0. You just look and see where is it above the x-axis and where is it below. Okay. All right, so any further questions about rational functions or polynomial inequalities or rational inequalities or any of that stuff before I move on to the next chapter? Okay, well, if you want to see me do more examples of these types of problems, please, please, I'm begging you to come to office hours today. Most of the time I just sit in there like on my own, twiddling my thumbs. So please come and let me be useful. Okay. So we're going to move on now to a new chapter. We're going to talk about something completely different. Okay. So let me start by laying sort of the groundwork for what we are going to talk about. We're going to talk about functions which we call exponential. Okay. You guys have probably seen an exponential function at some point in your life, but let me remind you what they look like and why we call them exponential functions. Okay. So it's a function of the form f of x equals a to the power x. Okay, so for example, f of x equals 2 to the power x, or 1/3 to the power x. Okay, things like this. So we just have a number, a, here, to a power, and the power is our independent variable, x. Okay, so what makes an exponential function exponential is that we have an x in the exponent. Okay, so the distinction that I want to draw here is that f of x equals x cubed is not exponential. Okay, and the reason is if we want to have exponential, we should have a power of x in the power, okay? We should have x in the power. Here we have an exponent, but this isn't exponential, okay? Because the exponent here is just a number, okay? So when I talk about an exponential function, I'm talking about having x in the power, or in the exponent, okay? So we have a number to a power of an exponent, as opposed to this function here, x cubed, we have a x to a number. Okay, that would just be a polynomial. Okay, so we call the number a the base, and we call the exponent the exponent. All right. So really quickly, we'll talk about the domain and range. So what is the domain of an exponential function? Well, we can plug in really any number we want, right? If we have 2 to the x, we can do like 2 to the -3, no problem, right? That would just be 1 over 2 to the 3. We can do 2 to the 0, right? That would be fine as well. It's just 1. And then we can do 2 to any positive number, right? We could do 2 to the, we could even do 2 to the 3/2, for example. Or we could even do 2 to the pi, okay? We can do any exponent, okay? It's not a problem. All right. And what about the range of an exponential function? I should have left myself a little bit more space here. Maybe I'll give myself some. Oh, I don't like that. Yeah, we'll move that down just a little bit. And I'll explain briefly why the range is going to be 0, infinity. Okay, if I imagine 2 to the x, right? Well, if I plug in something like really, really negative into 2 to the, maybe 2 to the -100, what's that going to be equal to? Remember, it's just going to be 1 over 2 to the 100, okay, right? Which, what does this number look like? Well, it would be 1 divided by something really, really large. This is very close to 0, but not 0. Okay, so when we plug in really, really negative numbers to these things, what's happening is actually just that we get a fraction, right? But the fraction is still a positive number, okay? There's no negative signs being introduced by these powers here, okay? So, basically, we can get numbers which are very, very close to 0. And if I were to plug in something else, something really large and positive, like 2 to the 100, we would get something really big. In fact, 2 to the x can be as big as we want, depending on what we plug in for x, right? You give me a number, and I'll give you an x value such that 2 to the x is bigger than your number. Okay, that's how that works. So that's just a bit about why the range is going to be 0, infinity. It's because by choosing x cleverly, I can choose an x that makes 2 to the x larger than any possible number. So that's why our cap is kind of positive infinity. And the reason our beneath cap is going to be, or our base, I guess, is going to be 0, is because I can make a fraction incredibly small, but if I divide 1 by something, I'm never going to get 0. Okay, I'm just going to get some fraction like 1 over a million, or 1 over a billion, or 1 over a trillion. But if I just keep going with that, I never actually hit 0. All right, I would never actually hit 0. Okay. So that's about the domain and range of an exponential function. And this should say a larger than 1. Typo there. So if you're using the skeleton notes, don't forget to change this to a 1. A should be larger than 1. Okay, so if we have a is larger than 1, then we're going to call that exponential growth, and let me show you why. So let's take, for example, geez, can't talk today, the function that we were just using. We'll use f of x equals 2 to the x. Well, we can plug in different values of x into this function. If we plug in 1, we would get 2 to the 1, which would be equal to just 2. If we plugged in 2, we would get 2 squared. That would be equal to 4. If we plug in 3, we would get 2 cubed. That would be equal to 8. If we plug in 0, we'd get 2 to the 0. And remember, anything to the power 0 is just 1. And now if we want to plug in these negative numbers, I already kind of explained how we do that. Well, if we have 2 to the negative 1, remember a negative power means we just move that to the denominator. This is just 1 over 2 to the power 1, and 2 to the power 1 is just 2. So this would be 1/2. And then if we plugged in negative 2, well, 2 to the negative 2 would be equal 1 over 2 squared, would be equal to 1 over 4. Okay, so let's plot some of these points. We've got 1, 2. That goes right there. We've got 2, 4. 1, 2, 3, 4. Oops, I went up too far. 1, 2, 3, 4 would be right here. And we've got 3, 8. So that's way up here. And we have 0, 1. We have negative 1, 1/2. So I don't know, right here maybe. And then negative 2, 1/4. So like down here. Okay? And if we were to fill in the gaps of this thing with a smooth curve, here's what it's going to look like. It's going to be basically looking like a Hot Wheels track ramp or a monster truck ramp. Okay, so this is what it looks like. And remember, what I said was that as we go very, very negative, right? What these look like is, say we look at like, the point negative 100. If we were to plug that in, we would get 2 to the negative 100 equals 1 over 2 to the 100, which is still larger than 0, but very close to 0. Okay, so that's what's going on the left-hand side, is we're just getting really, really close to the x-axis, but never touching it. And on the right side, we're blowing up, basically. We're going to positive infinity. Okay? And if you give me a height, okay, then I can tell you the x value such that the height of the function is going to be higher than your height, right? That's what it means for this function to be going to positive infinity, is I can find an x value that produces any height that I want. Okay, and the reason we call this exponential growth is typically we think of ourselves as moving to the right, okay? Typically, if we're talking about a time or a temporal process, we would put time on, I guess I'll just draw this with pink. Okay, sorry. We think of the temporal process as moving from left to right. Okay, that's how we naturally kind of think of things. When we read books, we read from left to right for the most part, with some exceptions. But for the most part, we move left to right as, you know, going forward in time, right? If you're on your computer and you're doing a download, right, then it moves left to right, okay, as the bar is getting bigger and bigger. Okay, so we think of time as going to the right, and so we say as time marches forward, as we go to the right, what is happening to the function? Well, it's getting very large. When something's getting large as time goes on, we call that growth. Okay, maybe this is just a bit obvious, so let's move on. I want to remind you guys really quickly about some exponent rules here. Let's see, what are they? We've already learned these, so I'm going to go through pretty quick. If we have a to the x times a to the y, we should add the powers. If we have a to the x to the y, then we multiply the powers. If we have a to the x divided by a to the y, and those both look the same, let me fix that. We have a to the x divided by a to the y, then that's a to the x minus y. A to the 0 is always equal to 1. If we have two numbers being multiplied together and we take the whole thing to a power, we can distribute the power. I'm going to call that 5a, and I'm going to call 5b a rule that you should just remember as well, which is that the same is not true for things like a plus b to the x. This is not equal to a to the x plus b to the x. Okay, why? We would have to FOIL x times. Okay, so that's 5b. And then finally, the last rule, we already saw this, it's a to the negative x is equal to 1 over a to the power x. So we make the power positive in the denominator. Okay, so these are rules for if a, b, x, and y are real numbers and a is larger than 0 and b is larger than 0, okay? All right. Oh yeah, one final note on number 6. We can also rewrite this as 1 over a in parentheses to the power x. So this might be the only new thing really in this whole section. It's just that we can rewrite 1 over a to the power x as 1 over a to the power x. right? Linguistically, it makes sense. But also mathematically, it's true. Any questions about these exponent rules? I think we already pretty much covered this, so if you need more practice with that, though, office hours would be a good time. Okay, so let me talk about exponential decay. So exponential decay is going to happen when our a value, okay, our base, is a number which is between 0 and 1, so something like 1/3, okay? And let's see why. All right, if I do 1/3 to the power x, and x is 1, then I would get 1/3, right? If x is 2, then I would do 1/3 squared, right? And 1/3 squared is actually going to be equal to 1/9, right? We would do 1/3 times 1/3. You just multiply across, right? The top you do 1 times 1 and get 1, and the bottom you'd get 3 times 3, you would get 9. Okay? And look what happened here. As we moved to the right, okay, as x went from 1 to 2, the height of our function went from being 1/3 to being 1/9. So the height of our function became less. Okay, so this is kind of showing you why when we have a number which is between 0 and 1, when we take larger and larger powers of it, the number is actually getting smaller. Okay, so let's try 0. Well, 1/3 to the 0 is just like with any other number equal to 1. And then if we were to do 1/3 to the negative first power, this would be equal to 1/3 to the negative first power. And if we have a negative power in the denominator, then we should move it to the numerator and make the power positive. And that would be equal to 3. Okay, so this just looks kind of flipped from the situation we had before. So let's plot these points. 1 comma 1/3, well, that's like, I don't know, right here. 2 comma 1/9 is like, I don't know, even closer to the x-axis. 0 comma 1. And then negative 1 comma 3. All right, so if we were to fill all this crap in with like a smooth curve, it might look something like this. Okay? Where this thing is going up to positive infinity, and this thing is going down to 0, but not reaching 0. Let me rewrite this. We'll write up to infinity. Okay, so we think as the temporal process as moving from left to right. So as we move from left to right, what's happening to the height of our function? Well, it's getting really, really small. It's shrinking, right? So we call this exponential decay. Right? If you think of like a, I don't know, something decaying, some kind of log in the forest maybe is decaying. Well, the process of decaying is basically, you know, it's getting smaller and smaller, right? It's getting eaten up by termites or whatever and getting smaller. And also gross. Okay, so that's what exponential decay is. It happens when our base value is a number which is between 0 and 1. So that's as opposed to growth, which occurs when our base value is larger than 1. Okay. By the way, what happens if our a value is actually equal to 1? Well, f of x would be equal to 1 to the power x. So let me ask, is this decay or growth? What do we think? Or something else entirely? What would happen if we just had 1 to the power x? Yeah, Savannah's got it. It's going to be constant. Why? Because you can just make the table, right? Try 1, 2, 3, 4, and you'll do on the right-hand side. We'll do 1 to the x. Well, 1 to the power 1 is 1. 1 squared, that's 1 times 1 is 1. 1 cubed, that's 1 times 1 times 1 is 1. All right, and so on and so forth. Okay, no matter what value of x we plug into 1 to the power x, we just get 1. So this function, if we were to graph it, it wouldn't even look like an exponential function at all. It would look like, just a flat horizontal line. Okay, so that's what's going on with 1. So we only say that it's decay if a is strictly less than 1 and strictly larger than 0. And we say that it's growth if a is strictly larger than 1. Okay, one more thing I want to talk about here, which is, let me give myself a little more space. If we see something like f of x equals 3 to the negative x, okay, we might initially think maybe this is exponential growth, since 3 is strictly larger than 1. But we have to be careful not to fall into this trap here, okay? We have to be careful not to fall into a trap. And here's why. When we defined exponential growth and decay, we assumed f of x was of the following form. We said f of x was going to be equal to some number a to the power x. And that's not in agreement with what we have written down up here. These are not of the same form. So, switch, we want to switch f of x, yes, okay, I know I'm done, to the right form. Well, we know f of x is equal to 3 to the power negative x, which is equal to 1 over 3 to the power x. That was one of our rules, right? And we said that this is also equal to 1 over 3, parentheses, to the power x. And now we see that a is actually not equal to 3. It's actually equal to 1/3. And since 0 is less than 1/3 is less than 1, we have exponential decay. Okay, so when we talk about exponential growth and decay, we want to make sure that we're writing things in the right form. Okay, we need to have some number a to a power x. Okay, a number a to a power x. If the power is negative, we have to rewrite a so that the power becomes a positive power. Okay, so that was what we did on this step here to the left of my red highlighting. Okay, we switched the form of 3 to the negative x to look like some number to the power x. Since that number was less than 1, we conclude that we have exponential decay. Okay. I'm out of time, so that's where we're going to stop for today. We'll finish up talking about exponents and exponential functions tomorrow. And I'm really happy because I'm actually kind of on track right now. So yay us. Anyways, that's it for today. So hope you enjoyed the lecture. That'll be all. Have a good day. Office hours start right now. So if you want to see some math, stick around. Yep, my pleasure.